Before you build anything serious with AI, an agent, a chatbot, a RAG pipeline, or an automation workflow, there's one thing that makes everything easier: understanding the language of AI. Because as soon as you start reading docs or experimenting with models, you realize the conversations around AI are built on a shared vocabulary. Words like embeddings, inference, context window, or quantization get used almost casually, but each of them carries a very specific meaning. And once those meanings click, everything else becomes clearer. AI stops feeling unpredictable. It becomes something you can reason about, optimize, and build with confidence. So let's start with the words you'll see the moment you step into real development work. A token is simply a piece of text that the model understands, and it's also the unit you pay for. Anytime you run summarization or feed long conversations into a model, tokens determine the cost and the time it takes to respond. That naturally leads into the context window, which is the model's temporary workspace. It decides how much information the model can hold onto within a single request. A 16,000 model can read a few pages. A 1 million token model can process entire books. And when you want the model to understand meaning instead of exact keywords, you use embeddings. These turn text into numbers that cluster similar ideas together, which is how semantic search and recommendation systems work. Then there's inference, the simple act of running the model to get an output. If you've ever waited too long for a response, you've experienced slow inference. As outputs get longer, developers rely on KV caching so the model doesn't recalculate everything from scratch with every word it generates. And when you need models to run on smaller hardware, you use quantization, a way of compressing the model so it becomes faster and cheaper to deploy. These ideas may sound technical, but they shape real decisions every day. Tokens influence cost. If your email summarizer uses 150,000 tokens per request, the bill grows quickly. The context window determines capability. A legal assistant that can't process a long contract becomes useless. Latency improves dramatically with KV caching when you build chat-like interfaces where each message depends on everything said before. And quantization decides whether your model runs on a lightweight server or needs a more expensive GPU instance. These aren't abstract concepts, they're constraints and tools you actively work with when building. But to understand why these details matter, it helps to zoom out for a moment. Machine learning replaces hard-coded rules with pattern recognition. Instead of writing an if statement for every case, you give the system examples and it learns what patterns matter. Deep learning builds on that by adding layers. With each layer, the model sees the data a little differently. Early layers detect simple features, deeper layers understand structure, meaning, and context. This layered understanding is why modern models can translate languages, classify documents, or write code. And it brings us to an important part of the conversation: neural networks and their parameters. A neural network is a chain of mathematical operations. Each connection inside it has a weight, a parameter that determines how information flows. Large language models have billions of these parameters. They form the model's internal knowledge and patterns learned entirely from data. More parameters generally mean deeper understanding and better reasoning, but they also bring higher compute costs and more engineering challenges, and the way these parameters are learned brings us to training. Training is the learning phase. Massive datasets are processed, predictions are made, errors are measured, and the parameters adjust. This cycle repeats millions of times, usually across large GPU clusters. Inference is the opposite. It's the execution of the final model. When you call an API or run a local model, you're doing inference. Training is slow and expensive. Inference needs to be fast and consistent, because it's what users experience, and both depend heavily on the data used to teach the model. Datasets are the examples a model learns from. Labels mark the correct answers. In supervised learning, like spam detection, each example comes with a label, spam or not spam. In unsupervised learning, the model discovers patterns on its own, like grouping users by behavior. And in reinforcement learning, the model receives feedback and learns through rewards, a method used to align LLMs with human expectations. Modern language models combine all of these stages, but even then, the model can struggle if the patterns become too specific or too vague. Overfitting happens when a model memorizes the training data instead of learning the underlying pattern. It performs well on examples it has seen, but poorly on new ones. Underfitting happens when the model never learns enough to begin with. The goal is balance, a model that generalizes well. And when we return to LLMs, the first place we see this balancing act is in how they use tokens. When an LLM reads your input, it doesn't see raw text, it sees tokens. And the number of tokens affects how fast the model responds, how much it costs, and how much context you can include. Prompt engineering is simply giving the model the structure it needs to perform well. Clear instructions, well-defined roles, examples, and formatting help reduce ambiguity. A well-structured prompt can transform the model's behavior completely. But when you need the model to deeply understand your domain, prompting alone isn't enough. That's where fine-tuning comes in. Fine-tuning takes a base model and adapts it to your world. Customer support teams fine-tune on past tickets. Legal teams fine-tune on case summaries. Companies fine-tune on product manuals and internal documentation. The result is a model that understands your tone, your terminology, and your rules, not because you prompted it well, but because it learned directly from your data. And once you combine fine-tuned understanding with retrieval of external knowledge, you get embeddings. Embeddings convert text into vectors, numerical representations of meaning. Texts with similar meaning sit close to each other in this vector space. Developers rely on embeddings for semantic search, recommendations, clustering, fraud detection, and most importantly, retrieval. Vector databases store these embeddings and make it easy to search for the most relevant information, and this leads naturally into one of the most powerful architectures in modern AI, RAG. RAG combines the strengths of embeddings with the generative power of large models. Instead of relying only on what the model learned during training, RAG retrieves relevant documents at runtime and feeds them into the prompt. This keeps the model accurate, grounded, and up to date. It's how tools like Notion AI, GitHub Copilot, and enterprise knowledge assistants deliver reliable responses, even when the information changes constantly. Even with retrieval, models can still hallucinate, not because they're broken, but because they generate the most statistically likely next token, not the most factual one. Latency is another practical factor. A slow model breaks user flow, especially in chat and real-time applications. Optimizing inference, caching, and model size all help reduce this. Underneath everything is the architecture itself. Transformers power language. CNNs excel in vision. RNNs help in sequential tasks. But large models need heavy compute, so developers use compression. Quantization reduces precision, distillation teaches a smaller model, and pruning removes unnecessary parameters. These techniques make large models practical, letting you deploy them on smaller servers or even locally. To understand whether your system is improving, you rely on evaluation metrics. Accuracy measures correctness. Precision and recall reveal how well the model handles imbalanced data. Loss tells you if training is progressing. Perplexity shows how confidently the model predicts text. These metrics guide every improvement, from training to fine-tuning to deployment. When you see how each of these ideas connects, tokens, embeddings, context windows, retrieval, architectures, compression, AI starts to feel like a system instead of a mystery. Every part supports the next, every term carries weight, and once you understand them, you don't just build with AI, you design intelligent systems intentionally. So the next time someone mentions inference, quantization, RAG, or KV caching, it won't feel like jargon. You'll know exactly what they mean and how to use them. Now you've seen how these core AI concepts actually show up in real development, from building agents to optimizing RAG to fine-tuning models for real-world products. If you want more content that breaks down AI and Web3 the way developers actually use them in real projects, clean code bases, and production systems, make sure you please subscribe to my channel and like this video. I publish detailed and explanatory videos to help you build smarter, ship faster, and stay ahead of the curve.